Hello, I welcome you all in this course on mechanical measurement systems. Today we will solve a few numericals related with the mechanical measurement system. Now starting with the numerical based on the first order system, the statement of the numerical is a signal described by the relation theta is equal to 3 sine 2t. This is theta I is equal to 3 sine 2t plus 0.4 cos 10t. This is the input signal. It requires to be measured by using a first order system having a time constant of 0.1 second. So lambda is 0.1. Develop expression for the corresponding output. So first order system is being used for the measurement, and we have to drive equation for the response of the instrument. First of all, here when we do this first order analysis of this type of input, cyclic input, we add only sine equations. So cos has to be converted into the sine, 3 sine 2t plus 0.4, or we can write minus 0.4 sine pi plus 10t, right? Lambda is equal to 0.1. Now let us take theta 1a. Now for this component, the amplitude ratio is 1 by under root omega square lambda square plus 1, right? And here in this case, the omega is 2. Omega is 2. In this case, omega is 2. Lambda is 0.1, right? So amplitude ratio is going to be under root 2 square 0.1 square plus 1, and that is going to be equal to 0.9805. It means the response of the system for this input, particularly for this input, the amplitude is going to be 0.9805 into amplitude here is 3, it is going to be 2.94. Okay, and regarding the phase lag phi is tan inverse omega lambda. This is phase lag, or phase angle is tan inverse minus omega lambda. Either way we can write. So phase lag is tan inverse 2 into 0.1, it is going to be 11.31 degree. So here, so A1, amplitude of A, and this is phase angle is 11.31 degree. Similarly, we can do for this. This is part A. Okay. Now for part B, amplitude ratio for part B, okay, it is going to be again 1 by 1 plus omega lambda whole square under root omega lambda whole square under root. Now here omega is 10 and lambda is 0.1, so it is going to be under root 1 plus tan into 0.1 whole square, and that comes to be 0.707. So here amplitude is attenuated by 0.707 and here it is 0.98, right? Because frequency is high. So when the frequency is high, then amplitude ratio will be low. Phi phase angle is equal to tan inverse omega lambda. What is omega? 10 into 0.1 is equal to 45 degree. And this, because it is amplitude is attenuated by 707, so 0.707 multiplied by 0.4 will give the amplitude, and that is going to be equal to, this is minus 4, so this is minus, so minus 0.283. Now we have amplitudes and phase angles for, or phase lag of responses in both the cases. Now here we can conclude that here the amplitude ratio of A, let us say RA is this much, amplitude of ratio A is this much, and this will give the amplitude of A dash or A. This is phase lag of A, this is part A. For part B, this is amplitude ratio RB, right? And amplitude in the part B is this, and phase angle in part B is this. Now we have 4 values for amplitude. This is for amplitude, phase, and this one is for amplitude, and this is for phase angle, right? And we can write the finalized equation as theta O, that is output. Now this is input signal. Now the output signal is going to be 2.94 sine 2t minus 11.31. This is the phase lag. Minus 0.283 sine 10t plus pi minus 45 degree, right? And now this is the final response of, now here we can see when the omega is high, the amplitude ratio of output and input is low. When the omega is low, when omega is only 2, the ratio has gone up to 0.98. Now this is an observation in this case. So lambda is equal to 0.1 in this case will give large measurement error, right? Larger measurement error. So now we will take another example. This is for the second order system. During the act of force measurement by a pressure transducer of diaphragm type. So during the act of force measurement by a pressure transducer of diaphragm type, the system is stated to have a natural frequency of 1000 Hertz. So natural frequency of the system is 1000 Hertz. Okay. And damping ratio 60%. So damping ratio 60% means zeta is equal to 0.6. Determine the frequency range over which the amplitude ratio corresponding to sinusoidal input deviates by maximum amount of 10%. So deviation is 10% in amplitude for sine response, for the sinusoidal input. So consider transducers to behave pressure transducer to behave as a second order system, right? So amplitude ratio in a second order system, the amplitude of a second order system can be expressed as 1 by, this is amplitude ratio, this m is the amplitude ratio, okay, is 1 minus r square whole square plus 2 zeta r whole square, where r is equal to omega by omega n. Now if we consider amplitude ratio as 1 by 1.1, right? Here, because it is a, we have to go for the amplitude ratio 1.1. So when it is 1.1, then we can put here m is equal to 1 1.1 and try to find the value of R because zeta is already known. It is 0.6. Right? If you simplify this equation becomes R raised to power 4 minus 0.56 R square plus 0.174 is equal to 0. Now here, if we take the solution of this equation, it has both imaginary roots, right? Both imaginary roots. So it implies that this is not a possible solution. Means we cannot go for m is equal to 1.1. Here also it is stated that the damping ratio is 0.6. So for damping ratio 0.6, output will never be 1.1 because we are getting roots here, all there are imaginary roots, right? So if there is a response of the system, so response m is not exceeding 1, it means. So we should go for 0.9 because deviation can be on both sides, plus 10% or minus 10%. So here m we can put 0.9. Once we are putting m is equal to 0.9, then we are getting another equation. Then this equation is about R raised to power 4 minus 0.56 R square minus 0.234 is equal to 0. Now let us take solution of this equation. This R square is equal to 0.56 plus minus under root 0.56 square plus 4 into 0.234 divided by 2. And this will give the R square value as 0.84. So we have replaced 1.11 by 0.9 and the equation is modified like this. R square we are getting 0.84. So R is equal to under root 0.84 and it is going to be 0.916. We will not take negative because W by W omega n can never be negative, right? So this is R is 0.916. So 0.916 means if you multiply this by 1000, we will getting the omega as 1000 multiplied by 0.916, it is going to be 916. This is not hertz, this is cycles per second. So it is 916. 916. 916. It is 916 cycle per second. So this omega n is 1000 hertz. So, so omega is 1000 hertz. So this 9.916 is multiplied by hertz and we are getting 916. So this is the answer for this numerical. Now another numerical will take up about the estimation of error. This is the power measurement is to be conducted by measuring voltage and current across a resistor R. So there is a resistor R. Voltage and current has to be measured across the resistor R. So there is a ammeter, right? R parallel to R, there is a voltmeter, and voltmeter will have certain resistance. Right? The voltmeter has internal resistance 1000. So this Rm is 1000 ohms. Okay. Calculate the nominal value of the power dissipated in R and uncertainty for the following conditions. So how much power is dissipated in R? So I is equal to, let us say that the current is splitted in two parts, I is equal to I1 plus I2. This is total current, it is I1 and this is I2. And potential difference between these two is E. So I is equal to E by R plus E by Rm. Okay, because they are connected in parallel, so E will remain common. Or we can say that current here I1 or E by R, I1 is equal to I minus E by Rm. Right? Because R we do not know. R we do not know, but we have measured the I1. Right? So E, the value of E is with us, value of I is with us, and value of Rm is with us. So we have made two measurements. Value of R is approximately 100, it is approximately 100 ohm. It is approximately not correct one. Right? Calculate the nominal value of power dissipated in the R. What is the nominal power dissipated in the R? So for dissipation of the power, and Rm is 1000 plus minus 5%, or I'll write here Rm is 1000 plus minus 5% ohms. Current is 5 ampere plus minus 1%, and E is 500 volts plus minus 1%. Okay, so P is equal to simply EI. So E is 500 into 5. 500 into 5. But this I is shared between, because this I is splitted. It is going to Rm and one I is going to the resistance. All I is not entering here, it is I1 and I2. So power dissipated will be by I1 only. So P is going to be this minus 500 square by 1000, E square upon R. This power dissipated by this will be subtracted. So final power is going to be 2250 watts. That is the power dissipated by R. So PR is 2250 watts. Now we have to find uncertainty in the measurement. So power is a function of, here the power is a function of E, I and Rm, because we calculated P is equal to EI minus E square upon Rm. So it is a function of EI and Rm. Right? Now we will take del P by del E. Now the equation remains same. EI, P is equal to EI minus E square upon Rm. Right? Now del P by del E is going to be equal to I minus 2E by Rm. Now del P by del I is going to be E, and del P by del Rm is going to be, this is 0 minus E square by Rm square, and this will become plus. Now uncertainty in the measurement of power, UP. Uncertainty in the measurement of power is going to be I minus 2E by Rm whole square, uncertainty in the measurement of E square plus E square I square, right? And we'll use plus, this is E square is del P by del I uncertainty in the measurement of I. Then del P by del Rm square, so E square by Rm square whole square, E square R square whole square, and then error in Rm whole square raised to power 1 by 2. Now we can put, because respective values are known to us, so here we can put the values. Uncertainty in the measurement of power is 5 minus 2E. 2 times E is 500 divided by Rm 1000 into 5 square, because UE 1%, so 500 volts and 1% of 500 volts is 5. Okay, it is E square is 25 into 10 to power 4 into 25 into 10 to power minus 4 plus 25 into 10 to power 4 divided by 10 to power 6 whole square into 2500 raised to power 1 by 2. If we simplify this, then we will be getting UP is equal to 16 plus 25 plus 6.25 raised to power 1 by 2 multiplied by 5. And final uncertainty is 34.4 watts. If you take percentage wise, now percentage wise uncertainty is 34.4 divided by 2250 into 100, and that is going to be 1.53%. And uncertainty in the measurement is lowest in, or bearing of the error in the measurement of resistance of the voltmeter is minimum. So if we are now here we are measuring 100, R is approximately R is equal to 100 ohms approximately, and voltmeter resistance is 1000 volts, 1000 ohms. If we were measuring R of 500 ohms and voltmeter resistance is 1000 ohms, then this error would have increased because substantial part of the current would have been going to the voltmeter. Contrary to this, if we were measuring 5 volts, 5 ohms and the voltmeter resistance was 1000 volts, this would have further reduced. Okay. So this is about this example of error analysis. Now one more example we'll take about the design of venturimeter. Venturimeters are used for the flow measurement, for metering the flow through a pipe. In this example, a venturimeter is to be used to measure maximum flow rate of water of 3.5 kg per second. That is a maximum flow rate, 3.5 kg per second. That is the mass flow rate of water at 20 degrees centigrade. So temperature is also given at 20 degree centigrade, right? The throat Reynolds number is to be at least 10 to power 5. Minimum Reynolds number at throat has to be 10 to power 5. It can be 10 to power 6, 10 to power 7, 10 to power 8, but minimum Reynolds number has to be maintained 10 to power 5. The upper scale limit is to be selected to corresponding to the maximum flow rate. Determine the venturi size and the maximum range of differential pressure. So venturi size and the maximum range for differential pressure. So it is a little design problem. It's not totally numerical. It is a little design problem, because here some informations are to be required. For example, density of water. Density of water, let us assume 1000 kg per meter cube. Density of the water. Viscosity of the water is 0.01 poise or 0.001 Pascal seconds. Okay, and Reynolds number here. Reynolds number are going to be rho Vd d by mu. Mu is the viscosity, V is the velocity of water in the pipe, d is the diameter of the pipe, and rho is the density of the pipe. And we know that VA and rho is mass flow rate by continuity equation, and A is pi by 4 d square. So Reynolds number can be written as mass flow rate multiplied by d divided by pi by 4 d square mu. So m by A will give the rho v. So rho v is replaced by ma. So this will give 4m divided by pi d mu. And that has to be greater than or equal to 10 raised to power 5. Now here, mass flow rate is given 3.5 kg per second, right? Mu is also with us, right? And what is required? D. D we can find from here. So D, in order to find D, that is D maximum is equal to 4 into 3.5 divided by pi into 0.001 into 10 to power 5 into 100 is equal to 4.45 centimeters. We have converted meter because normally the pi diameter is the order of a few centimeters. So we have converted meter into the centimeter. It is 4.45 centimeters. If you reduce the diameter, the Reynolds number will increase. Because don't go by this formula. Mass flow rate, because here if you reduce the diameter, it appears the Reynolds number will reduce. But when you are reducing the diameter, velocity will increase. If you go by this formula, mass flow rate is constant. So if you reduce the diameter, Reynolds number will increase. So in any case, if we take the diameter is smaller than this, the Reynolds number will be more than 10 to power 5. But this is not a standard size in the market. 4.445. It is difficult to get such type of venturi. So pipe into throat section, if we go for the standard venturi, it is going to be 5 centimeter and 2.5 centimeter. So 5 centimeter into 2.5 centimeter. And if you go for the throat diameter 2.5 centimeter, definitely the Reynolds number will be higher than 10 to power 5, right? Now, with this selection of 2.5, the Reynolds number will be modified as 10 to power 5 into 4.45 divided by 2.5, 1.78 into 10 to power 5. This condition is satisfied. For this venturi, coefficient of discharge is going to be 0.9752. For this Reynolds number, 57, this is 9752. Now we have coefficient of discharge. A1 area here, which is the diameter of the pipe, is 5 centimeter. Area 2, diameter of the pipe 2.5 centimeter. Coefficient of discharge is already with us. We can make use of this equation for the actual mass flow rate through the venturi meter, that is rho CD A1 A2 divided by under root A1 square minus A2 square under root 2G P1 minus P2 divided by rho G. Right? So G and G will be considered. Okay. So this is the mass flow rate, actual mass flow rate from this venturi meter. A1, A2 we can easily calculate because the diameter of one pipe is 5 centimeter, another pipe diameter is 2.5 centimeters. Rest of the values are known, but we do not know the value of P1 minus P2. So this is only a known in the entire equation, and if you put the values, respective values, then you will be getting P1 minus P2 as 25.143 kilopascal. So whatever value you get from this equation divided by 1000, then you will be getting the pressure drop as 25.143 kilopascal. right? So this is the actual design of the venturi for the flow measurement. Pipe diameter 5 centimeter, venturi throat diameter is 2.5 centimeter, and pressure drop is going to be 2.5143 kilopascal for the flow measurement of 3.5 kg per second. I hope you have enjoyed this course, and in the following week you will have exam of this course. Best of luck for examination. Thank you.